Right. Good afternoon, everyone. Thank you all for coming. I'll try to make it very brief. Am I still using his time or? Oh, it started already. I'll try to be very brief. I know my presentation was, I was asked to reduce by 50%, so I'm skipping slides. Don't mind me, I can send you the full presentation at a future time. I'm really excited to come here and share the experience. The last 12 years, we've been pushing the concept of hybrid structure, particularly timber steel hybrid structure was the concept that we have been really pushing on. And then with that type of analysis and work that we have done, we have showed using different innovative systems in a place like, for example, high seismic zone like Victoria and Vancouver, we can really push the building height limit. The advantage of being from research side, I don't have to worry about if it's going to be compliant with the code. It's going to be a limitation because those type of testing and concepts with time, with testing and validation, and with the seasoned engineers here that are sitting here, they will come up with a solution. So mainly I was trying to push the concept and the limit of these hybrid structures. Number of funders were supporting us through this project. A number of highly qualified students that have contributed to this research I like to acknowledge, and number of collaborators that have been making. This is some from the council's website in January 2001. I know this is something that is continuously changing. So the concept of tall building is evolving. This is something that we have started with 6-story in Canada, and then pushing the limit to 12-story now. And then with the research that we are undertaking, we're trying to push it to 20 stories, important, more being in a high seismic zone. And this is an exciting time to be. And the deal breaker, I think the FP innovations, they should be acknowledged. When they push that CLT handbook, it's been adopted in the States, where the deal breaker. And then in Canada, also a number of different demonstration projects were done with this type of timber and concrete hybrid type of structures. So the first project that we undertook, where we were looking at steel moment resisting frame and with CLT infill. So then what we have realized from this type of analysis and work that we have done is the CLT infill does indeed contribute significantly to the lateral resistance, right? So the CLT infill contributes to the lateral resistance. Then we needed to sort of develop what type of design, as Eric showed, that overstrength and ductility factor as per the Canadian code. So what code would you use if you have to use this type of hybrid structures, right? So would you follow the timber code, steel code, or NBC, where we take the conservative R0RD factor? So that was sort of the driving factor why we push this type of hybrid structures. And then from our analysis, we're using nonlinear time history analysis, looking at 3-story up to 12-story for this type of structures. Then we identified what is the appropriate R0RD factors. And for this, we strictly followed the FEMA P695 detailed nonlinear time history analysis method to derive. And then one important factor that is that came from this research, that's not even part of the code, is even that R0RD factor is period dependent, right? So most of the code we have now, we have R factor of 8. But that R factor of 8 for a 2-story structure, 6-story, 12, and 20 will have different implication, right? So that's sort of one of the recommendations from this project we came up with, is we need to come up with R0RD factors that should be period dependent. And then with this, we looked at also displacement-based design as part of performance-based design, and then also looked at energy-based design to design this type of structures. So the next project that we looked at is to push the limit to up to 20-story. So instead of now conventional shear wall building, now we're using shear wall coupled with some type of innovative dampers, right? So those type of replaceable shear link, and then the demand also on the hold downs is significantly increasing. So that connection became the bottleneck, the critical factor. And then for this type of structure, then we proposed beyond that replaceable shear link to use the concept of BRB. And then I'll be happy to let you know that recently with Dr. Thomas at UNBC and core brace with Brent. So we have done testing. So in the future presentation, we'll be reporting the data that we have. Now, from the conceptual design and implementation, we took it to detailed performance-based design for this type of innovative systems. So one critical factor when we're looking at this type of system is to look at the damping factor, right? So what damping factor do we use? So for the most part, there's a very conservative damping factor that we are using. But now the more this innovative system that we are introducing, what damping factor? So that's part of the big design uncertainties that we have, like for wind and an earthquake type of design. And then also with this type of toll structural and hybrid system that we have noticed and then that I didn't present today is not only now seismic is an important factor. Now with hybrid system, we have a more efficient, lighter structure, and then wind become also an important factor. Even in a location where it's high seismic zone, then wind will become an important factor. So the design, we're looking at it sort of now is in a silo. There's a performance-based design for wind, performance-based design for earthquake, and so forth. So now we have to be looking at it more in a holistic way, performance-based design that accounts in a multi-hazard sense. Even if we bring fire component to it, so earthquake, wind, and fire, it becomes in a performance-based multi-hazard design framework. So I feel the design guidelines that we have, the approaches that we have are sort of taken in a silos. That's sort of, I feel, the next phase of the design process. They have to bring these different elements and then find out what is the best alternative design that will satisfy the requirement. So, conservatively here we can say 2%. So one interesting from this type of analysis that we have, most of these papers that I have collected and identified in this structure, they have done in situ measurement. So from there, around 2.5% could be a conservative number to use. Often, like for wind, that could be governing. And if we use that for seismic also, the hysteretic and other energy dissipating type of damping, that will be additional damping that can be neglected, but then that's inherent damping the structure will have. And then one other important factor, as from timber industry, we don't look at it from design point of view, is soil structure interaction. So at the moment now we start pushing the building height, soil structure interaction will become a very critical design component. That's going to affect the response of the structure. So then the more we're making it lighter, more flexible, and pushing the building height limit, more design factors, more questions are coming in the picture that we're trying to address that I don't know the answer at this point. So then once we finish that coupled wall project, the next one we looked at is to use outrigger as a concept. So with this outrigger type of system, looking at, so what you see here, the outrigger beams and to the exterior columns are connected with energy dissipator damper shape memory alloys. So it has a good recentering capability, and in terms of resilience in post-earthquake, that will have very small residual drift. So part of the work that we have undertaken for this type of system is trying to optimize and then find out where is the best location of these outriggers, right? So for this type of outrigger system, for this type of couple system that we have, we use some mathematical models to represent as a surrogate model, and then we use the detailed finite element model to verify and indeed find where the location of that outrigger. So one of the issues that is coming from this outrigger type of structural system that we have, now our exterior columns will be subjected to this external axial load, right? So now instead of column beam made out of beam, glulam, then we have to start using steel structure, or we have to start looking at belt outrigger system to distribute the load. So the more we try to find the solution, we have more questions that we haven't answered yet. But the concept of outrigger has been applied for different type of structures extensively. I feel bringing this concept now to steel timber structure will help us to push the building height limit without compromising safety. So finally, I'd just like to share my thoughts with you. Like currently what we're working on is where we're now trying to bring structural functionality and an aesthetics into our design process. We've seen this number of different presenters. Number of these diagrid structures have been constructed. So when we look at this structure, we're looking at it from 5-story, 10, 15, and 20 stories, right? So then we're using initially pure timber only, and or optimizing, trying to find the right balance between, say, timber and timber diagrid, between a steel core, timber diagrid, or timber core and steel diagrid. And then also optimizing the diagrid, like it's going to be every 2-story, 4-story, 6-story, and so forth, right? So that's part of our current optimization and design process that we are trying to develop within this performance-based design criteria to push the building height limit at the same time in a high seismic zone, meet some aesthetic requirement to make those buildings more attractive. And in addition, with this type of outrigger diagrid system, also by breaking the outrigger beam sort of in the middle and then introducing some type of slit damper that we can introduce that will contribute to the seismic resistance, additional seismic resistance, additional energy dissipation is what is important. At the end, so with this type of design process that we're looking at, from the core to the hold downs, and then all these energy dissipations in an optimized way should give us what will be the best design alternative for our structure. Thank you very much.